Hello, the purpose of this video is just a brief introduction into ionic bonding. There are a couple of different ways that atoms can combine with each other. One way is through ionic bonds, and another way is through covalent bonds. Ionic bonds tend to occur between atoms that are metals, such as on the left side of the periodic table, and nonmetals, such as atoms or elements that are on the right side of the periodic table. And that is because of the amount of valence electrons that they have. So first of all, let me just briefly talk about what ionic bonding is. What happens is we have to look at the valence electron. This is sodium. If we look at sodium, sodium is in group 1. It's an alkali metal. And everything in group 1 tends to have one valence electron. That is signified by this dot. Remember, valence electrons are the electrons on the outer energy shell. If we see here, sodium has 1, 2, 3 energy levels. This is the third energy level, and it only has one valence electron. Chlorine over here has 1, 2, 3 energy levels. If I look at its outer energy level, it has 1, 2, 3, 4, 5, 6, 7. Sorry, I should have looked right here, 7 electrons. So this only has 1, and this has 7. Now basically, the orbitals are confusing and they have different shapes, and we've already gone over those, but really all we need to know is chlorine really wants one more electron to become 8. If I had 8 electrons, here's chlorine. If I had one more electron, it would be just like a noble gas argon. Sodium really wants to give away one electron, so it could be like neon. Now think about it. It's easier for sodium to give away one electron, to be like neon, than it would be for sodium to gain many electrons, to be like argon. That's why these substances over here, when they only have 1 or 2 valence electrons, tend to lose them. Whereas over here, when they have 7 valence electrons in the halogens, or 6 in the chalcogens, or 5, they tend to gain electrons because it's easier to gain a few to become like the noble gas. And of course, this is all dealing with electrons and different energy levels. So, an ionic bond is formed when a metal gives up an electron and becomes positively charged, and a nonmetal gains an electron and becomes negatively charged. And then those charges create an electrostatic force and make them stick together, basically, for lack of a better term. So let's look at this. Sodium gives up one electron. That electron attaches to chlorine right here. And when that happens, when sodium gives up that one electron, see how it's negatively charged? Sodium is now positively charged. Why is that? Because there are a bunch of protons that are positively charged. Normally you have the same amount of protons as electrons. Let's look at this. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. And I have 11 protons. These protons are positive, the electrons are negative. But if I lose one electron, now I only have 10 electrons and I have 11 protons. That is why this forms a +1 ion. It's a positively charged ion. Now over here, chlorine gains an electron. That electron is negative, so it gains a -1 charge. So we have positive and negative, and then they bond together. There's a term for a positively charged ion. First of all, when an atom gives up an electron or gains an electron, it is called an ion. It's a specific term. If it is a positively charged ion, it is called a cation. If it is negatively charged, it is called an anion. Now keep in mind, sometimes these could give up one electron, sometimes two, sometimes three. It depends on the element and where it's at in the periodic table. So it could be a +1 cation, a +2, a +3. And over here it could be a -1 anion, a -2, or a -3, and so on. Now, of course, this is all based off of valence electrons. So, quick review. These metals tend to lose electrons. These nonmetals gain electrons because of their valence electrons, and they combine, forming something called an ionic compound. Now, ionic compounds actually are neutral. They have no charge. If I look at this here, this is +1, this is -1, and when they combine, it's a zero charge. So ionic compounds have no charge, but cations and anions have charges. So let's look at what happens when these form. By the way, this is table salt, sodium chloride. When ionic compounds form, they create special structures. These are called crystalline lattices or crystalline structures. Ionic compounds tend to form solids. See how these are solid crystals. And this is actually what table salt looks like. It's a crystal structure. Look at the chloride anions and the sodium cations. Notice how it's a 1-to-1 ratio. We only need one chloride to every one sodium. This is actually something called a chemical formula. Now this is a little bit different than molecular formulas. Molecular formula is something like H2O. In water, there actually are 2 hydrogen atoms bonded with 1 oxygen atom. So that's a specific amount of atoms bonded together. This would be a molecular formula. Those are covalently bonded. In chemical formulas, this is just a ratio. You're not actually going to find 1 chloride and 1 sodium bonded together. It's simply saying it's a 1-to-1 ratio, 1-to-1. And we see that in the structure where it's a 1-to-1 ratio and it forms a specific lattice crystalline structure. Now, I say that because sometimes you might have 2 anions and they bond with 1 cation, and it's not going to always be a 1-to-1 ratio. The ratio can change, and that changes the shape and that changes the properties of the ionic compound. So, these ionic compounds form solids, the crystalline lattices, and these are actually very strong bonds. These bonds are so strong it's really hard to break them apart because of that electrostatic charge. And so these actually have high melting points, basically high melting points like boiling points. You're going to have to actually give them a decent amount of energy or heat to break them apart. We can go down here and kind of look at this little chart here, melting points and boiling points. And these are molecular compounds. These are ionic. Notice how the ionic compounds, the melting point and boiling points, this is in Celsius, are much higher than the molecular compounds. So you have to put more energy or heat into these to break them apart than into these. And these are solids here. We see that basically, these are liquids or gases. And we don't need to go into detail, but sometimes on tests in intro chemistry, they'll ask about melting points and boiling points and crystalline lattices and things like that. So it's good to know. Now, here's another thing about ionic bonds, ionic compounds. They tend to dissociate in water. So if I take this and I put it in liquid, it will break apart again into the chloride anions and the sodium cations. The water will actually, the H2O will break these bonds apart. And you're probably thinking, well, why? You just said it. You have to put a lot of energy into this and heat it up to make it melt and all of that. Well, there's a reason for that. Let's go ahead and look at water. Here's H2O right here. Now, we haven't gone into this yet, but H2O is actually something called polar covalent. So these are covalent bonds, but you notice that actually there's a slight positive charge on the hydrogens and a slight negative charge on the oxygen. So one side of these is charged a little bit different than the other side. Wait a minute. Remember that these ionic compounds have a negative and positive charge? So when I take this entire thing and put it in water, what happens is the negative side of water starts pulling at the positive sodium cations and kind of tearing them away. And the positive side of water, the hydrogens, are pulling at the chloride anions and tearing them away. So it's like ripping this apart because of the charges. You can kind of see that right here. So another thing to remember on our test is that many ionic compounds, most ionic compounds are soluble. They dissociate in water. Solubility just means if I put it in water, it will break apart. And that is because of the charges and the polar covalency of H2O. And keep in mind, it depends on the liquid you're putting this in. Normally, people always put things in water, and water is polar covalent, but I could put it in alcohol or some other liquid and it would have a different effect depending on the type of liquid I'm using. So let's go ahead and look at our list of things we need to know. They form crystalline structures, which we've seen. These are lattices. They have high melting and boiling points. They are solids, so that means they're hard and rigid and brittle. They're decently brittle, so they're not malleable like metal. They have chemical formulas that kind of show ratios, not specific numbers of atoms. And here's the other thing that we sort of skipped over. They're good conductors of electricity when dissolved in water. So we know that they can dissolve in water, but now that you put it in water, you can actually run a current through the water. See how we have these charge plates, negative, positive, and we hook it up to a battery, and we could hook it up to a light right here. And what is going to happen is, right here, you remember how I told you it's already soluble, it dissociated in water, so now we have positive cations floating around, and we have negative anions. So if I put a current through this, see how the positive cations are going towards the negative plate, and the negative anions are going to the positive plate, and that's actually electricity. That's a current flowing through here. And if we hooked all this up, the light bulb would actually turn on. And the crazy thing is, I could put some other liquid in here, and it would not, if it's not an ionic compound, if it's not soluble, it actually would not make the light glow. So there's a term for that, electrolyte. You're going to see that on a test. It'll ask about electrolytes. Electrolytes are simply something that if I put it in water, it'll disassociate and it'll allow electricity or current to flow through it. So ionic compounds are electrolytes. Ionic compounds are good conductors of electricity when dissolved in water. Okay. And yet again, I just wanted to kind of show you this chart to show you the amount of energy that's in these lattices. They're pretty high. This is kilojoules per mole. So how much energy do I have to put into a mole of this to break it apart? And notice, this is lithium combining with fluorine. Lithium combining with chlorine. If I look at my periodic table, here's lithium, here's fluorine, here's chlorine, bromine. Here's bromine, and here's iodine. So actually, it's going to be high at the top of the group and decrease a little bit as I go down with lithium. And that is because fluorine's more electronegative. If you look at periodic trends, electronegativity decreases as I go down this group. And we don't have to memorize these numbers. All we really have to know is this is a decent amount of energy that I have to put into this. Let's look at our trend here. Notice how aluminum, this is a metal trend, and it's in group 13 or 3 and has a 3 plus charge. Notice how I got to put more energy. This is higher. And this is a crazy number here. It's very high. That's because as this charge increases, as the charge increases on this, it's actually going to make the ionic bond stronger. And if that ionic bond is stronger, it's going to take more energy to then break it apart. So those charges do make a difference. Okay, that's just a real brief introduction to ionic compounds. We're going to do a lot more with it. I just want you to yet again realize pretty much what it is. Remember that they form crystalline structures and lattices. They have high melting and boiling points, that they will dissociate and they are soluble in water because of how water is a polar covalent molecular compound. They can form electrolytes because they dissociate in water, and just basic ideas about their bond energies. I hope that helps you, and good luck on the test.